welcome to the Deep Dive. Today we are jumping into something truly fundamental. We're taking a deep dive into the very fabric of reality itself.
That's right. We're tackling, the biggest questions. What is the universe ultimately made of? And what are the fundamental rules that govern everything within it, from the smallest speck to, well, the largest galaxy?
Exactly. Our source material for this deep dive is a set of excerpts from a fascinating book that explores this ambitious, centuries-long quest for the ultimate theory of the cosmos.
Yeah.
Think of this as your shortcut to understanding some of the most mind-bending ideas modern physics has come up with, all broken down into hopefully accessible steps for you.
Our mission really is to unpack some truly wild concepts, the laws that describe the universe on the grandest possible scales, and then the laws that govern the absolutely tiniest things we know.
Right.
And crucially, we'll look at where these two incredibly successful sets of laws spectacularly clash, and how scientists are proposing radical ways to bring them together into a single, unified picture.
And we are really going to try and take our time here, make sure these ideas land, because the core challenge we'll explore right up front is this fundamental conflict. On one side, you have the laws governing the universe on a grand scale. Think planets orbiting stars, galaxies colliding, black holes, the expansion of the cosmos itself. Einstein's theory of general relativity describes this beautifully.
Absolutely. And on the other side, you have the laws governing the absolutely minuscule atoms, protons, electrons, the quarks inside them, the forces holding them together. This is the realm of quantum mechanics.
And it works incredibly well for the small stuff.
Incredibly well.
But here is where it gets weird. Both theories are brilliant, proven right by countless experiments within their own domains.
Sure.
But when you try to apply them together at extreme conditions, like inside a black hole, where enormous mass is squeezed to an infinitely small point,
Or at the literal moment of the Big Bang, when the entire universe was packed into this microscopic nugget.
the math just breaks down. The equations give nonsensical answers. Infinity pops up where it shouldn't.
It's like they speak different languages, they describe different aspects of the world perfectly on their own, but become gibberish when you try to translate one directly into the other in these extreme scenarios.
This incompatibility isn't just some, academic curiosity. It's a profound puzzle at the heart of physics.
Right.
It tells us our understanding is incomplete, and it screams out for a deeper, more fundamental set of laws that work for everything, everywhere, all the time. Okay, so before we fully dive into that clash, let's start with the very foundation. What is stuff actually made of? The building blocks.
Yeah, it's a question that goes back millennia, really. The ancient Greeks, over 2,000 years ago, had this remarkably insightful idea. They thought you could keep dividing matter until you reached tiny, uncuttable ingredients. They called them atoms, meaning uncuttable.
Which, for the time, was a fantastic guess.
Yeah.
Really ahead of its time.
Absolutely. But as we learn much, much later, atoms weren't the end of the story. By the early 1930s, through the groundbreaking work of people like Thomson, Rutherford, Bohr, Chadwick.
A whole cast of characters.
Exactly. We understood that atoms could be cut. They had parts.
Right. We got that familiar picture.
Huh.
A tiny, dense nucleus at the center, made of protons and neutrons, surrounded by a cloud of electrons zipping around.
And the quest didn't stop there. Physicists kept pushing, using ever more powerful technology, like particle accelerators.
Giant machines smashing things together.
Pretty much. Smashing bits of matter together at incredible energies, trying to recreate conditions like those right after the Big Bang to see what comes out.
And they found even more fundamental ingredients, didn't they?
They did. This deep quest revealed 6 types of quarks. You've got your up and down quarks, which make up protons and neutrons.
Made everyday ones.
Right. And then the slightly more exotic ones. Charm, strange, bottom, and top quarks.
Always loved those names.
Me too. They also found heavier cousins of the electron, like the muon and the tau particle, and different types of these really ghostly particles called neutrinos.
Neutrinos just fly through everything almost.
Almost everything, yeah. What's also fascinating is that for every one of these particles, there seems to be an antiparticle partner.
Antimatter.
Exactly. Same mass, but opposite charge and other quantum properties. So an electron's antiparticle is called a positron. A proton has an antiproton.
And when matter and antimatter meet, boom.
Ooh, is right. They annihilate each other. Their mass converts entirely into pure energy following that famous equation E mc up u.
Which is why we don't find big chunks of antimatter just, lying around.
Precisely. It meets its matter partner pretty quickly and vanishes in a flash of energy.
Okay, we've looked at the tiny. Now let's pivot to the grand scale. the laws of motion and gravity, and how our everyday experience, our intuition, totally breaks down when we think about speed.
Yeah, our common sense intuition about motion is always about relative speed. Saying you're moving at 10 miles per hour only makes sense compared to something else.
Like the ground or the road.
Or the air or the car you're in, exactly.
Yeah.
There's always a reference point.
Like that analogy from the source material.
Yeah.
If you're on a train passing another train on parallel tracks, right?
Mm-hmm.
And you can't see the scenery outside, maybe the windows are fogged up, you might not actually know if your train is moving or the other train is moving.
Or if you're both moving at different speeds, if the ride is perfectly smooth, you just feel the relative motion between the two trains. You can't tell who's really moving.
This suggests there's no absolute fixed stationary point in the universe, no cosmic signpost saying you are here and not moving. It's all relative.
Exactly. And that idea seems, well, fairly reasonable.
Yeah, seems fine. Until you run into a big problem that puzzled physicists for a long time. A problem that led directly to Einstein's work.
The conflict arose from a monumental breakthrough in the mid-1800s by James Clerk Maxwell. He did this incredible thing, unifying electricity and magnetism.
Right, into electromagnetism.
Yes, the electromagnetic field. And his equations showed that disturbances in this field, things like light waves, always travel at a fixed, constant speed.
And that fixed speed turned out to be the speed of light.
The speed of light. Light is an electromagnetic wave, and Maxwell's theory said its speed is always the same no matter what, no matter how the source of the light is moving or how the observer is moving.
Now that is completely different from our everyday experience.
Totally different. Think about throwing a baseball, right?
Okay.
If your friend throws the ball at, say, 20 feet per second, and you run away from them at 12 feet per second.
The ball's only coming towards me at 8 feet per second.
Right. 20 minus 12 is 8. Your speed affects the speed of the ball relative to you. That's just common sense.
But with light, this doesn't happen. If your friend shines a flashlight, it doesn't matter if you run towards the light, away from the light, or just stand still.
You will always measure that light traveling at the same speed, about 670 million miles per hour. It's a constant. Your own motion makes no difference to the speed of light you measure.
That just feels wrong, intuitively.
It does. And this seemingly simple fact, the unchanging speed of light, is where our common sense about space and time crashes headfirst into reality. It demanded a total revolution in how we think about these fundamental concepts.
And that's where Einstein's special theory of relativity, published in 1905, comes in.
Exactly. It's built on just two core ideas, two postulates. One, there's no absolute standard of rest. Motion is only relative.
The train idea.
Right. And two, the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source.
Okay. Seems simple enough.
Simple on the surface? Maybe.
Yeah.
But these two ideas, when you follow their logical consequences, lead to truly bizarre but experimentally confirmed effects on space and time, especially as you get close to the speed of light.
One of the strangest is that simultaneity is relative. Things happening at the same time.
Right. Events that happen at the exact same moment for one observer might not be simultaneous for another observer who is moving relative to the first.
How does that work?
Well, the source gives a great analogy. Imagine two presidents signing an important agreement at opposite ends of a long train car. They sign at the exact same time according to someone on the train.
Okay.
Light signals from the pens hitting the paper reach the person in the middle of the train car simultaneously. But for someone standing on the platform as the train rushes by.
The train is moving relative to them.
Exactly. So from the platform observer's perspective, the light signal from the president at the back of the train has further to travel to reach the midpoint, which has moved forward, while the signal from the front has less distance to cover. They don't arrive simultaneously for the platform observer.
So at the same time, depends on how you're moving.
It does. At normal speeds, this difference is ridiculously tiny, undetectable. But near light speed, the effects are huge. It means there's no single universal now that everyone in the universe agrees on.
Wow. Okay. What else?
This also gives us time dilation. Time literally passes slower for a moving object compared to a stationary one.
Slower,
but only from the perspective of the stationary observer.
Right, like that light clock analogy. You imagine a clock where time is measured by a photon bouncing between two mirrors. If that clock is just sitting there, the photon bounces straight up and down. Tick, tock. But if the clock is moving sideways relative to you,
the photon has to travel diagonally to hit the opposite mirror because the mirror has moved.
A longer path.
Longer path for the photon. Since the speed of light is constant, A longer path means it takes more time for each tick from your perspective. So you see the moving clock running slow.
And this isn't just theoretical.
Not at all. We see this in the real world. There are these fast-moving subatomic particles called muons, created high in the atmosphere when cosmic rays hit.
Okay.
They have very short lifespans. Based on their known lifespan when they're at rest, they shouldn't have enough time to reach the Earth's surface before decaying. But many of them do.
Because time is running slower for them.
Exactly. From our perspective on Earth, their internal clock is ticking slower due to their high speed, so they live longer and make it down here.
But, and this is crucial, right?
Yeah.
From the muon's perspective, its lifespan feels totally normal.
Absolutely crucial. It doesn't feel time slowing down. Everything in its own frame of reference, including its own decay process, slows down uniformly relative to us. It experiences its normal amount of life.
This leads to the famous twin paradox, doesn't it?
It does.
Huh.
If one twin, let's call him George, travels on a spaceship at near light speed away from his twin sister Gracie, who stays on Earth, and then George turns around and comes back, George will find he has aged far less than Gracie.
He's effectively time traveled into her future.
He has. And the reason George knows he's the one who underwent the journey, even though motion is relative, is because he felt the acceleration.
Right, the G-forces, using the jetpack, turning around.
Exactly. He felt the forces needed to speed up, turn, and slow down. Gracie, who stayed put on Earth, mostly, felt none of that significant acceleration, so the symmetry is broken, and George is the younger one upon return.
Okay, so time slows down. What about space?
Another effect is length contraction. Objects appear shorter in the direction of their motion when measured by an observer who is in relative motion to them.
Shorter, like squashed.
Only in the direction of motion, yeah. Like if Jim is standing by the road measuring Slim's incredibly fast car as it zips past, Jim would measure the car as being slightly shorter end to end than Slim measures it when it's parked.
Again, tiny effect normally, huge near light speed.
Exactly. So special relativity forces us to abandon the idea of separate absolute space and absolute time. They are interwoven
Into space-time.
into a single dynamic four-dimensional fabric called space-time. 3 dimensions of space, 1 of time.
And here's the truly mind-bending insight that comes from that. Einstein proposed that all objects are always traveling through this space-time fabric at one constant speed.
Yes.
The speed of light.
But how can I be moving at the speed of light if I'm sitting still?
Because you're not moving at the speed of light through space. If you're sitting perfectly still relative to me, all your motion through space-time is directed into the time dimension. You're traveling through time at the maximum rate. You're aging.
Okay.
If you start moving through space, some of that constant total speed through space-time gets diverted into motion through the spatial dimensions. It's like turning a car. You divert some forward motion into sideways motion.
So you have a total speed budget through space-time equal to the speed of light. You can spend it all on moving through time if you're at rest in space, or spend some on moving through space, which means you have less speed left for moving through time.
Exactly. The faster you move through space, the slower you move through time. That's time dilation again, seen from this space-time perspective.
And a photon of light.
A photon travels at the maximum speed possible through space. That means it uses up its entire space-time speed budget on spatial movement. It has no speed left to travel through time.
So time doesn't pass for light.
From the photon's perspective, no time elapses between when it's emitted and when it's absorbed. A photon that left a distant star billions of years ago is, in a sense, still brand new when it hits your eye. It hasn't aged.
Wow. Okay. My brain hurts a little. And this also gives us E equals mc squared, right? The most famous equation ever.
It does indeed. It's another profound consequence of special relativity. It revealed that mass m and energy E are fundamentally linked. They're like different forms of the same underlying stuff, interchangeable like different currencies.
And the exchange rate.
The exchange rate is the speed of light squared. C chi, since C is a huge number, 670 million Farrell 4, C squared is astronomical. This means even a tiny amount of mass contains or can be converted into a colossal amount of energy.
Which is the principle behind nuclear bombs and nuclear power.
Exactly. Converting just a little bit of mass into energy releases immense power.
So special relativity gave us this new unified view of space-time, dealing with constant speed and relative motion. But it immediately created a problem with the existing theory of gravity, Newton's theory.
Right. Newton saw gravity as a force acting instantaneously across any distance. You pull, I feel it right away, no matter how far apart we are.
But special relativity says nothing, not even information or influence. can travel faster than the speed of light.
Exactly. So, in Newton's picture, if the sun suddenly vanished, poof,
The Earth would instantly fly off its orbit at the same moment.
which violates special relativity's speed limit. There needed to be a delay. Newton's gravity was incompatible with the new rules of spacetime.
And it was Einstein, yet again, who came up with the solution about 10 years later.
Yes, with his general theory of relativity in 1915. And GR didn't just tweak Newton's theory, it completely revolutionized our understanding of gravity.
It wasn't a force anymore.
Not in the traditional sense. General relativity says space and time aren't just a passive, fixed stage where events happen. They are active players. They are dynamic, capable of being warped and curved.
And that warping is gravity.
Precisely. The presence of matter or energy literally warps or curves the fabric of space-time around it.
Okay, here comes the classic analogy, the bowling ball on the stretched rubber sheet.
It's a helpful visual, yes. You put a heavy bowling ball on the sheet, and it creates a dip, a curve in the surface.
And if you roll a smaller ball bearing nearby, it doesn't get pulled directly towards the bowling ball by some invisible string.
No, it just follows the curve of the dip in the rubber sheet. It rolls downhill along the curve, appearing to be drawn towards the bowling ball.
So in the universe, the sun's mass warps the space-time fabric around it.
Like the bowling ball warping the sheet.
And the Earth, moving through this warped space, follows the curved paths, the shortest or easiest path in this curved geometry.
Which we perceive as the force of gravity pulling the Earth into orbit around the sun. It's just following the shape of space-time.
Okay, pause on that rubber sheet analogy, though, because the source material points out a really important distinction.
Yes, it's crucial. In the analogy, the bowling ball makes the dip because Earth's own gravity is pulling the bowling ball down onto the sheet.
Right. The analogy uses gravity to explain gravity, which isn't quite right.
Exactly. The analogy helps visualize curvature, but the reason for the warping in general relativity is different. The sun doesn't warp space-time because some other gravity is pulling on it. The mere presence of the sun's mass and energy is the source of the warping. Warp space-time is gravity.
Got it. That's a fundamental shift. And GR says changes in this warping, like if the sun exploded, these gravitational waves,
They travel outwards at the speed of light.
solving the conflict with special relativity.
Exactly. If the sun vanished, we wouldn't feel the loss of its gravity instantly. We'd feel it about 8 minutes later, the same time it takes the last light from the sun to reach us.
General relativity also incorporates something called the equivalence principle.
Right. Which says, essentially, that the effects of gravity are indistinguishable from the effects of being in an accelerated frame of reference.
Like feeling pressed back into your seat when a car accelerates hard.
Yes, or when you're in a rocket taking off from Earth. That feeling of being pushed down feels exactly like gravity. Einstein realized these sensations are equivalent.
Or like being on one of those spinning amusement park rides, the Tornado or Gravitron. You feel pressed outwards.
Yes. And that outward push feels just like gravity. It's why you could, in principle, create artificial gravity in a spinning space station in deep space. The acceleration provides a gravity-like effect.
Just as gravity warps space, it also warps time.
It does. The stronger the gravitational field, the slower time passes relative to a region with weaker gravity.
So if I were, very carefully, lowered on a cable towards the sun,
Your clock would run measurably slower compared to someone like Gracie, staying farther away where the sun's gravity is weaker.
and this isn't just theoretical either. GPS relies on this.
Absolutely. GPS satellites orbit high above Earth, where gravity is weaker than on the surface. Their clocks naturally run slightly faster due to general relativity. They also run slightly slower due to their speed because of special relativity. You have to account for both effects to keep the GPS system accurate.
Wow. And general relativity wasn't just theoretically elegant. It made predictions that were confirmed, right? Things Newton's theory couldn't explain.
Yes, a major one was explaining a tiny, previously mysterious anomaly in the orbit of Mercury. Mercury's orbit slowly shifts over time in a way Newton's theory couldn't fully account for. General relativity's prediction matched the observation perfectly. That was a huge triumph. So, okay, we have general relativity. It beautifully describes gravity and space-time on large scales. Planets, stars, galaxies, the universe itself.
Sure.
And we have quantum mechanics, which brilliantly describes particles and forces on tiny scales, atoms, electrons, quarks.
Sure.
They are both incredibly successful theories, verified again and again, until you try to use them together at the extremes. The very big meeting, the very small.
Like inside a black hole or at the Big Bang.
Exactly. Then they break down. And quantum mechanics itself is just, well, profoundly weird.
You hear that a lot. People say you can use the math, make predictions, but truly understanding it.
At a gut level, at a soulful level, as the source puts it, very few people claim that. It really means our everyday language and intuition, built on the macroscopic world we see, just fail completely at the microscopic level.
So where did this weirdness start to show up?
One of the first major clues came from Max Planck around 1900. He was trying to solve a problem with how physics predicted energy should behave in heated objects, like inside an oven.
That was the problem.
Classical physics predicted that such an object should emit an infinite amount of energy, especially at high frequencies, like ultraviolet light, which is obviously wrong. Ovens don't vaporize you with infinite energy. This was called the ultraviolet catastrophe.
Right, that sounds bad. How did Planck fix it?
He proposed something radical. He suggested that energy isn't continuous like water flowing from a tap. Instead, it comes in discrete packets, or quanta, lumps.
Like coins instead of water.
Exactly. And the minimum amount of energy a wave could carry, its smallest coin, was proportional to its frequency. High frequency meant a high energy quantum.
How did that help?
Think of it like paying rent with specific denominations of money. If you only have $100 bills, you can't contribute to a total rent of, say, $50.
Right.
Similarly, the high-frequency waves in the oven couldn't contribute any energy at all unless they had enough thermal energy to create at least one of their very large minimum energy quanta. This limited the total energy at high frequencies and solved the infinity problem.
So energy is lumpy, quantized. That was the start.
That was a huge step. Then came another puzzle, the nature of light itself. Maxwell had shown convincingly that light behaved like a wave.
Spreading out, interfering.
Right, but then experiments on the photoelectric effect showed really strange behavior that didn't fit the wave picture.
That's when light hits a metal surface and knocks electrons out, right?
Yes. What they found was if you increased the brightness, the intensity of the light, you knocked out more electrons, which kind of makes sense for a bigger wave hits harder.
Okay.
But it didn't make the electrons come out any faster. Their speed, their energy didn't change with brightness.
That is weird for a wave. A bigger wave should give a bigger kick.
You'd think so. To make the electrons come out faster, you had to increase the light's frequency, change its color towards blue or violet.
So color mattered more than brightness for the energy of the electrons.
Exactly. And even stranger, below a certain minimum frequency, which depended on the metal, no electrons came out at all, no matter how bright you made the light.
Like a tiny wave just couldn't do the job no matter how many tiny waves you sent.
Precisely. The source uses a great analogy. Imagine children needing 85 cents to leave a warehouse, and you're throwing money at them.
Okay.
If you throw huge piles of pennies, nickels, and dimes, low frequency, low energy per coin, you might throw millions of coins, a huge total value, but no single child gets the 85 cents they need to leave.
Right. They can't pool the money.
But if you start throwing dollar bills, high frequency, high energy per coin, even just a few dollars are enough. $1 hits a child, they pay their 85 cents, and leave with change. The energy arrives in discrete lumps, not smoothly.
And Einstein explained this.
Yes, Einstein took Planck's quantum idea and applied it to light itself. He proposed that light isn't just a wave, it also comes in particle-like packets of energy called photons.
Like particles.
Yes, and the energy of each photon is directly proportional to the light's frequency, E(a)(f), where h is Planck's constant. So high-frequency light, blue, consists of high-energy photons, while low-frequency light, red, has low-energy photons.
So in the photoelectric effect, one high-energy photon can knock out an electron with high speed, but no amount of low-energy photons can do the job if they don't meet the minimum energy requirement.
Exactly. It perfectly explained the observations, but it left this deep puzzle. Is light a wave or is it a particle?
And the answer is?
The answer, bizarrely, seems to be
Yes, both. Welcome to wave-particle duality. Okay, my head is officially spinning now. How can it be both?
The double-slit experiment is the classic and maybe most mind-bending demonstration of this. You shine light through two narrow, parallel slits onto a screen behind them.
Okay, if light were just particles, like tiny bullets, you'd expect to see two bright lines on the screen directly behind the slits where the bullets went through.
That's what you'd expect. But that's not what you see.
What do you see?
You see an interference pattern, a whole series of alternating bright and dark bands spread out across the screen.
Like when water waves pass through two openings and interfere with each other, creating peaks and troughs.
Exactly like that. It's definitive proof of light's wave nature. The waves from each slit interfere, adding up where crest meets crest, bright bands, and canceling out where crest meets trough, dark bands.
Okay, so light is a wave. But what about the photons, the particles Einstein talked about?
Here's where it truly breaks our brains. You can lower the intensity of the light source so much that you're sending photons through the slits one by one.
So just one particle goes through at a time. There's nothing for it to interfere with.
You'd think so. But if you let these single photons hit the screen over a long period, recording where each one lands, slowly, painstakingly, they still build up the exact same interference pattern.
Wait, how? How can a single particle, going through presumably one slit or the other, interfere with itself to create a pattern that requires waves going through both slits?
That is the central mystery of quantum mechanics. It seems fundamentally impossible from our everyday perspective.
So what's the explanation? Or is there one?
The prevailing interpretation, pioneered by people like Richard Feynman, is perhaps even stranger. It suggests that in the quantum world, a particle, like an electron or a photon, doesn't just take one path from A to B.
Doesn't it?
No. It somehow takes every possible path simultaneously.
Every path, including paths that loop around Mars.
In principle, yes, though those paths usually have negligible contributions, but it definitely includes paths that go through the left slit, paths that go through the right slit, and even paths that somehow go through both slits at once.
That does not compute.
I know. For large objects, like baseballs, the contributions from all these weird paths effectively cancel each other out through interference, leaving only the single classical trajectory that follows Newton's laws. That's why we don't see baseballs taking multiple paths.
Okay.
But for microscopic particles, these multiple paths are significant. The probabilities associated with each path interfere, leading to the observed interference pattern, even for a single particle. The particle interferes with its own possibilities.
And the strangest twist of all, if you try to watch.
If you try to detect which slit the particle actually goes through, say, by placing a detector near one slit, maybe shining a tiny light on it,
You find out which pass it took.
you do. But the very act of observing, of measuring, inevitably disturbs the particle. It interacts with your detector. And that interaction forces the particle to choose just one path it goes through, either the left slit or the right slit, not both.
And what happens to the pattern on the screen?
The interference pattern vanishes. You just get two bands like you'd expect for classical particles. The act of observing changes the outcome. It collapses the wave of possibilities into a single reality.
The quantum world is changed by looking at it.
Fundamentally, which ties directly into another cornerstone of quantum mechanics, the uncertainty principle, usually associated with Werner Heisenberg.
Right. You can't know everything precisely at the same time.
Exactly. Specifically, you can never simultaneously know both the precise position and the precise momentum, which is related to speed and direction, of a particle.
The more accurately you measure its position.
The less accurately you can possibly know its momentum, and vice versa. There's a fundamental limit, a trade-off.
And this isn't just because our measuring devices are clumsy.
No, it's not about technological limitations. It's an inherent property of nature at the quantum level. It implies that everything, at its core, has a minimum amount of unavoidable quantum jitter or fuzziness. Things are never perfectly still or perfectly located.
Okay, so we have general relativity for the large gravity as the curvature of space-time works great.
Yeah.
And we have quantum mechanics for the small particles, forces, wave-particle duality, uncertainty, probability waves, works incredibly well for atoms and particles.
Check.
And they fundamentally clash when you try to combine them at extreme scales, like the Big Bang or black holes. GR needs smooth space-time, QM is jittery and probabilistic.
Right. They just don't mesh mathematically or conceptually at those points. We need a new theory, a unified framework that can handle both gravity and quantum effects simultaneously.
A quantum theory of gravity.
That's the holy grail. We need something that works everywhere, especially in those high-energy, ultra-dense conditions where both theories are important.
And this is where string theory enters the picture, proposing a really radical new idea about the fundamental building blocks, right?
It is. It's perhaps the most developed candidate we have for such a theory. The core idea of string theory is that the universe's most fundamental ingredients are not zero-dimensional point particles. Like electrons or quarks are usually pictured in standard physics.
Not points. Then what?
Instead, they are unimaginably tiny, one-dimensional vibrating filaments, like incredibly small rubber bands or loops of string.
So everything protons, electrons, quarks, photons, all the particles we know. They aren't fundamental points. They're just different ways these tiny strings are vibrating.
Precisely. Just like the different ways a violin string can vibrate produce different musical notes.
Higher pitch, lower pitch.
Exactly. The different resonant vibration patterns of these fundamental strings correspond to the different particles and forces we observe in the universe. The string itself is the fundamental entity. Its vibration pattern determines its apparent identity as, say, an electron, a photon, or a quark.
That's a huge shift in perspective. Where did this idea come from?
Interestingly, string theory actually started out in the late 1960s and early 70s as an attempt to describe the strong nuclear force, the force that holds quarks together inside protons and neutrons.
Okay, so it wasn't initially about gravity.
Not directly, but then in 1974, physicists John Schwartz and Joel Shirk, and independently Tamiaki Yonea, made a stunning realization. They were studying the properties of these vibrating strings, the different notes they could play, and they found that one particular vibration pattern had exactly the properties predicted for the hypothetical particle that should carry the force of gravity, the graviton.
Whoa. A massless particle with the right spin.
Exactly. It popped right out of the mathematics of vibrating strings. This was the light bulb moment. String theory wasn't just a theory of the strong force. It seemed to be a quantum theory that automatically included gravity.
So it had the potential to unify gravity with the other forces described by quantum mechanics, to bridge that gap between GR and QM.
That was the incredible promise. It seemed to naturally contain both quantum mechanics and general relativity. The challenge ever since has been working out the details and extracting precise, testable predictions from the theory, because the mathematics involved is incredibly complex.
Now, the source material mentions that the natural scale for these strings, related to how stiff or tense they are, is unbelievably tiny, the Planck length, which is like 10^35 meters. And their natural energy scale is likewise huge, the Planck energy.
Yes, the tension in these strings is thought to be enormous.
So how does the theory, based on such high energies, explain the particles we actually see, which are incredibly light compared to the Planck scale, like electrons and quarks?
That's a fantastic question, and the answer involves that quantum weirdness again in a really crucial way. Remember, the uncertainty principle implies everything has a minimum quantum jitter.
Yeah, things can't be perfectly still.
Well, these strings also experience this unavoidable quantum jitter. And here's the surprising insight. The calculations show that the energy associated with this fundamental quantum jitter of the string is negative.
Negative energy. How does that work?
It's a purely quantum mechanical effect. But this negative energy from the jitter does something amazing. It largely cancels out the huge positive energy coming from the string's enormous tension and its vibrational energy.
So the jitter cancels the tension.
To a large extent, yes. It's like having a huge positive number, tension energy, and a huge negative number, jitter energy, that almost perfectly balance. This means the lowest energy vibration patterns of these strings end up with relatively small positive net energies.
And those small net energies correspond to the masses of the light particles. We actually observe electrons, quarks, neutrinos, photons.
Exactly. The masses we see are like the tiny leftovers after this near perfect cancellation between huge positive and huge negative quantum energies. For the specific vibration pattern identified as the graviton, the cancellation is perfect, giving it exactly zero mass, which is required for a force particle like gravity that travels at the speed of light.
That's incredible. So the existence of the light particles we see depends critically on this bizarre negative energy from quantum jitter.
According to string theory, yes. It's a deep connection between quantum uncertainty and the particle spectrum.
String theory also seems to handle some problems that point particle theories have when you try to combine them with gravity.
Yeah.
Something about infinities.
Yes. In standard quantum field theories, particles are treated as mathematical points with zero size. If you try to calculate interactions involving gravity at extremely short distances, these point particles lead to uncontrollable mathematical infinities. The calculations blow up.
But strings aren't points.
Exactly. Strings have a minimum size, roughly the Planck length. They have a spatial extent. You can't probe distances smaller than the string itself.
So what happens if you pump more energy into a string, trying to make it probe smaller scales?
Unlike a point particle, which would just probe deeper, pumping energy into a string doesn't make it a sharper probe. Instead, the extra energy makes the string oscillate more wildly and effectively grow larger. It smooths things out at the smallest scales.
This inherent fuzziness, the minimum size of the string, prevents those infinities from appearing.
That's the idea. It naturally regulates the short-distance behavior of gravity in a quantum context, which is a major theoretical advantage.
String theory is also often called superstring theory. What's the super about?
The super refers to supersymmetry. This is a theoretical symmetry principle that proposes a deep connection between the two fundamental classes of particles we know: fermions, matter particles like electrons and quarks, and bosons, force-carrying particles like photons and gluons.
What kind of connect?
Supersymmetry predicts that for every known fermion, there should exist a corresponding boson superpartner, and for every known boson, there should be a fermion superpartner. These superpartners would have the same mass in a perfect unbroken supersymmetry, but differ in their spin property.
So an electron, fermion, would have a superpartner called a selectron, boson, and a photon, boson, would have a photino, fermion.
Exactly, those kinds of names, yes. Supersymmetry is mathematically very elegant and actually required for the internal consistency of most string theories. It helps cancel out certain mathematical anomalies.
And it has other benefits.
Yes. One intriguing consequence is related to the strengths of the fundamental forces. At everyday energies, the electromagnetic force, the weak nuclear force, and the strong nuclear force have very different strengths.
Right.
But if you calculate how these strengths change as you go to much higher energies, like in the early universe, standard physics shows they get closer but don't quite meet at a single point.
They almost unify.
Almost. But if you include the effects of supersymmetry in the calculations, assuming the superpartners exist,
They unify perfectly.
they appear to unify exactly at a very high energy scale. This beautiful unification is considered strong circumstantial evidence in favor of supersymmetry and, by extension, string theory.
But we haven't actually seen any of these superpartner particles yet.
No, we hasn't. If supersymmetry exists in our universe, it must be a broken symmetry at the energies we can currently access. This means the superpartners must be much heavier than their ordinary counterparts, requiring more energy to create than our current particle accelerators like the Large Hadron Collider can provide. Finding them is a major goal of future experiments.
Okay, and then there's the whole mind-bending aspect of extra dimensions. String theory seems to require more than the 3 spatial dimensions, up, down, left, right, forward, back, that we experience. Why?
That's another crucial ingredient. It turns out that for string theory to be mathematically consistent specifically, for certain quantum probabilities to add up correctly and not give nonsensical negative values, the strings need more room to vibrate than just our familiar dimensions provide.
So the math just doesn't work in only 3 spatial dimensions.
For the most promising versions of string theory, like superstring theory, the math works best in a total of 10 space-time dimensions, 9 spatial dimensions, and 1 time dimension.
9 space dimensions.
Yeah.
But we only see 3. Where are the other 6?
The idea, going back to the 1920s with work by Theodore Kaluza and Oscar Klein, even before string theory, is that these extra dimensions might be curled up or compactified into an incredibly tiny size.
Too small for us to notice.
Exactly.
Mm-hmm.
Perhaps as small as the Planck length we discussed earlier, a billionth of a billionth of a billionth of an inch or something like that. Completely undetectable with current technology, maybe even in principle.
Like the garden hose analogy from the source.
That's the classic analogy. From far away, a garden hose looks like just a one-dimensional line. You can only move forward or backward along it.
Right.
But if you get very close, like an ant walking on it, you realize there's another dimension, the circular dimension wrapped around the hose's circumference. The ant can walk along the length, but also around the circle.
So our universe could be like that hose.
Yeah.
With 3 large extended dimensions that we see, and 6 other dimensions curled up into some tiny shape at every single point within those large dimensions.
That's the picture string theory suggests. To fully specify a location in such a universe, you'd need to give its coordinates in the 3 large dimensions we know, and its coordinates within the tiny, curled-up 6-dimensional space that exists at that point.
Wow, that makes you wonder, could those tiny dimensions ever change? Could one of them somehow expand and become large?
That's a fascinating possibility that cosmologists consider within string theory frameworks. Perhaps the reason we have 3 large spatial dimensions is related to some process in the early universe where only 3 dimensions expanded, while the others remained small.
And the shape of those curled-up dimensions matters?
Critically, it's not just that there are 6 extra dimensions, their specific geometric shape is crucial. String theory suggests these extra dimensions are curled up into complex shapes, known as Calabi-Yau manifolds or Calabi-Yau spaces.
Calabi-Yau, Sounds complicated.
They are mathematically very complex. But the precise shape, the number of holes, the way it twists and curves directly determines the allowed vibration patterns of the strings within those dimensions.
And the vibration patterns determine the particles.
Exactly. So the geometry of the hidden, curled-up dimensions dictates the fundamental properties of the particles and forces we observe in our large dimensions. Things like the number of families of quarks and leptons, their masses, the strengths of the forces, all these fundamental parameters of our universe are, in principle, encoded in the shape of the extra dimensions.
So if we knew the exact shape, we could predict the properties of our universe.
That's the ultimate goal. The
Yeah.
problem is, mathematically, there seem to be a huge number of possible Calabi-Yau shapes, maybe 10 or 500 or even more. Figuring out which one, if any, corresponds to our universe is a massive challenge.
As physicists explored string theory more deeply, one of the most surprising and, frankly, bizarre discoveries was the existence of unexpected connections called dualities.
Yes, these dualities revealed profound relationships, showing that seemingly completely different versions of string theory or different descriptions of the universe within the theory could actually be mathematically and physically identical, equivalent.
Giving the same results even if they look different on the surface.
Precisely. One incredible example is the large-small radius duality, sometimes called T-duality. It applies when you consider one of the extra dimensions to be curled up into a simple circle.
Yep.
The duality suggests that a universe where this circular dimension has a very large radius, let's call it r, is physically indistinguishable from a universe where the circular dimension has a very tiny radius, specifically 1r, when measured in fundamental Planck units.
Wait, let me get this straight. A universe with a huge extra dimension curled into a circle behaves exactly the same as a universe with an infinitesimally small extra dimension curled into a circle.
That's what the duality says. It seems completely counterintuitive. Doesn't the size of a dimension seem like the most basic property you could measure about it?
Yeah, how can big be the same as small?
The reason comes back to the unique properties of strings, which don't exist for point particles. Strings can do two things in a circular dimension. They can vibrate, carrying momentum related to their vibration energy.
Okay, vibration modes.
But they can also wrap around the circular dimension, like a rubber band stretched around the garden hose. This wrapping contributes to the string's energy based on how many times it wraps the winding number and the radius of the circle.
So there are two types of energy modes, vibration modes and winding modes.
Exactly. Now, if the radius r of the circle is very large, it takes a lot of energy to wrap a string around it, long distance, but the vibration modes can have low energy. Waves fit easily.
That makes sense.
If the radius r is very small, it takes very little energy to wrap around it, short distance, but the vibration modes become high energy. Waves are squeezed.
Okay, I see the inverse relationship.
The duality shows that the complete set of possible energy states, and thus the possible particle masses and charges, you get from all combinations of vibration and winding modes in a universe with radius r is mathematically identical to the set of states in a universe with radius 1r, simply by swapping the roles of vibration modes and winding modes.
So the physics, the particles, the forces, everything you could measure is exactly the same, whether the dimension is huge or minuscule.
Yes. It means there's a minimum effective sized space in string theory. You can't distinguish experimentally between a dimension smaller than the Planck length and one larger than it because of this duality. It fundamentally challenges our classical notion of distance at these scales.
That's mind-bending. Are there other dualities?
Oh, yes. Another major one is mirror symmetry. This applies to those complex Calabi-Yau shapes for the 6 extra dimensions. It was discovered that pairs of completely different-looking Calabi-Yau shapes, topologically distinct, different numbers of holes in certain dimensions can nevertheless give rise to exactly the same physical laws in the large dimensions.
So two different shapes for the hidden dimensions can produce the identical universe that we see.
Exactly. They are mirror images of each other in terms of the physics they generate, even though the geometries themselves look totally unrelated. It's like having two incredibly complex machines with completely different internal workings that somehow produce the exact same output.
What does that imply? Does it help with calculations?
It can, immensely. Sometimes a calculation that is incredibly difficult or impossible to perform using one Calabi-Yau shape becomes surprisingly simple when you use its mirror partner shape thanks to the duality. It provides powerful mathematical tools.
But it also suggests something profound about space itself, doesn't it? That the exact geometry might not be as fundamental as we thought.
It does. It suggests that the physics is perhaps more fundamental than the specific geometry that realizes it. And it ties into another radical idea from string theory, that the fabric of space itself can undergo dramatic transformations, even tearing and reconnecting.
Space can tear. Wouldn't that be a catastrophe in general relativity, causing singularities?
In classical general relativity, yes, tearing the fabric of space-time would likely lead to physical infinities and disasters. But string theory seems to allow for certain types of space-tearing transitions to occur smoothly without physical problems. Again, it comes down to strings not being points. The finite size of the string acts like a sort of shield or buffer. The source uses an analogy, figure 11.6, where a string looped around a collapsing throat in space can prevent a singularity from forming. Its spatial extent smooths out the pinch point.
So strings allow space to change its fundamental shape, its topology, in ways that were forbidden before.
Yes. Calculations in string theory show that it's possible for one Calabi-Yau shape to continuously deform, tear in a controlled way, and then repair itself into a completely different Calabi-Yau shape, maybe even its mirror partner. All while the physics described by the theory remains consistent and well-behaved.
Like a donut shape smoothly transforming into a beach ball shape, as one analogy puts it.
Exactly. This involves complex processes where spheres of certain dimensions within the Calabi-Yau space collapse down to points, while spheres of other dimensions might grow, fundamentally changing the structure of the hidden space, but doing so without breaking the laws of physics, thanks to string theory.
These duality discoveries must have been crucial, because initially, physicists had found not one, but 5 different versions of superstring theory, right?
That's right. In the mid-1980s, there was this explosion of progress, but it led to 5 distinct, mathematically consistent superstring theories living in 10 dimensions. Type 1, type IIA, type IIB, and 2 heterotic types, E8 by E8 and SO32. It was confusing which one, if any, described our universe.
Seemed like an embarrassment of riches, or maybe a problem.
It did seem like a problem, but then, starting in the mid-1990s, physicists, led by figures like Edward Witten, began discovering these powerful dualities connecting all 5 theories.
They weren't separate theories after all.
No. The dualities showed they were just different facets, different descriptions of the same underlying fundamental theory, viewed under different conditions or approximations.
How does that work? Like different perspectives on the same object?
Exactly. For instance, one type of duality relates theories at strong coupling to theories at weak coupling. The coupling constant is a measure of how strongly strings interact. Calculations are usually only possible at weak coupling, where interactions are rare.
Okay.
The duality showed that if you took, say, the type I string theory and imagined turning up its coupling constant, making interactions strong, where calculations become impossible, it actually transformed into and became equivalent to the heterotic SO32 theory at weak coupling.
So seemingly different theory emerged when you pushed the first one into territory you couldn't calculate directly.
Precisely. Another duality showed that if you took the type IIA theory at strong coupling, something amazing happened. A new 11th dimension appeared, and the theory turned into an older theory called 11-dimensional supergravity.
An 11th dimension? I thought it was 10.
The 5 string theories were formulated in 10 dimensions, but this duality revealed a deeper connection to an 11-dimensional theory. It suggested that the 5 10-dimensional string theories, plus 11-dimensional supergravity, were all just different corners or limiting cases of a single, mysterious, underlying theory in 11 dimensions.
And this underlying theory is what Witten called M-theory.
That's the one. The M is famously ambiguous. Maybe it stands for mother, mystery, membrane, matrix. Witten never said definitively.
Like the blind men and the elephant analogy. Each string theory was describing just one part of the larger M-theory elephant.
That's a perfect analogy. M-theory is believed to be the more fundamental structure from which the 5 string theories emerge as different approximations.
And M-theory isn't just about strings.
No. While strings, which are one-dimensional objects or one-branes, are central, M-theory also includes other types of fundamental extended objects called p-branes, where p indicates the number of spatial dimensions the object has.
So like membranes.
Exactly. Membranes would be 2 branes. M-theory also contains 3 branes, 4 branes, up to 9 branes. These branes play a crucial role in the theory and its dualities. It's possible that our entire visible universe could be confined to live on a 3-brane embedded within the larger 11-dimensional space-time of M-theory.
Okay, so M-theory emerges as our leading candidate for the unified theory, potentially connecting gravity and quantum mechanics, strings, and brains, all within an 11-dimensional framework potentially linked to 10-dimensional strings. How does this potentially revolutionary framework connect to the big observational questions in physics like understanding black holes and the origin of the universe?
Black holes are a key testing ground. As we said, they are predicted by Einstein's general relativity regions where space-time is so warped by gravity that nothing, not even light, can escape.
And GR predicts that all the matter that falls into a black hole gets crushed down to an infinitely dense point at the center, a singularity.
Yes, a point of infinite density and infinite space-time curvature, where the laws of GR itself break down. GR also suggests black holes can, in principle, exist at any size, any mass.
And that small black holes should behave in some ways like elementary particles, right?
Yeah.
Having only mass, charge, and spin, the no-hair theorem.
That's right. This always hinted at a deep connection between black holes, gravity, large scale, and particles, quantum mechanics, small scale. String theory provides a way to make this connection much more concrete.
How so? You mentioned something about space tearing earlier.
Yes. Remember those topology-changing transitions allowed in string theory where spheres in the extra dimensions can collapse? String theorists like Andrew Strominger and Kumar Vafa, and later others, made remarkable progress by studying specific types of black holes within string theory.
What do they find?
They found that for certain types of black holes, they could precisely count the number of possible underlying quantum states, the number of ways strings and branes could be configured that would correspond to that black hole's macroscopic properties, mass, charge.
Counting the microscopic details.
Yes, and they found that this microscopic count perfectly matched the formula for the black hole's entropy, a measure of its disorder or information content that had been derived decades earlier by Jacob Bekenstein and Stephen Hawking using completely different semi-classical arguments combining GR and QM.
It sounds like a major success, matching the entropy from two different directions.
It was a landmark achievement for string theory. It showed the theory could reproduce a key quantum property of black holes from first principles. Furthermore, remember those space-tearing transitions where a 3D sphere collapses?
Mm-hmm.
Calculations showed that this geometric event in the curled-up dimensions corresponds exactly to a specific type of black hole losing all its mass and charge and smoothly transforming into a massless elementary particle like a photon or graviton, which are specific string vibration modes.
So, a direct calculated transition. Black hole evaporates completely, leaves behind a particle, and string theory describes it smoothly.
Exactly. It provides a quantitative link between these seemingly disparate objects, resolving the endpoint of black hole evaporation for these specific cases in a way GR alone cannot.
What about the singularity at the center of a typical black hole, like the one formed from a collapsing star? Does string theory resolve that?
That's still a much harder problem. String theory seems to resolve some types of singularities, like the ones involved in space-tearing transitions, but the singularity at the heart of a realistic black hole remains a deep mystery. Applying string theory calculations directly at that point of potentially infinite curvature is extremely challenging, and we don't have a definitive answer yet.
And Stephen Hawking's work also showed black holes aren't completely black, right?
Mm-hmm.
Hawking radiation.
Yes, using quantum field theory in the curved space-time background of a black hole, Hawking famously predicted that black holes should slowly emit thermal radiation, now called Hawking radiation. They aren't truly black, but glow faintly.
And this means they slowly lose mass and evaporate over incredibly long time scales.
Exactly. Smaller black holes should be hotter and evaporate much faster than large ones. Detecting this faint radiation directly is extremely difficult, possibly impossible for astrophysical black holes, which implies that very low-mass black holes, if they were formed in the early universe, probably aren't around anymore unless they started out quite large. String theory provides a microscopic basis for understanding the entropy related to this radiation, but the evaporation process itself is still being studied.
Okay, let's turn to the other extreme. Cosmology and the Big Bang. The standard model of cosmology is incredibly successful.
It is. It tells us our universe began from an extremely hot, dense state about 13.8 billion years ago and has been expanding and cooling ever since.
And the evidence is strong.
Overwhelmingly strong. The expansion itself, the abundances of light elements like hydrogen and helium, and especially the cosmic microwave background radiation, CMB.
The afterglow of the Big Bang.
Precisely. It's radiation left over from when the universe was about 380,000 years old, hot and dense, but cool enough for the first atoms to form. Before that, the universe was an opaque plasma. Once atoms formed, photons could travel freely, and the CMB is the snapshot of those photons, now cooled by the expansion of the universe down to just a few degrees above absolute zero.
And its properties match the Big Bang predictions perfectly.
In exquisite detail. It confirms the Big Bang picture back to that early time, but if you try to extrapolate even earlier, winding the clock back towards time zero...
The universe gets smaller, hotter, denser.
Yeah.
Insanely so.
Right. As you approach the very beginning, you reach conditions of temperature and density far beyond anything we can create in labs. Eventually, you reach the Planck time, an unimaginably tiny fraction of a second after the bang, about 1043 seconds.
And at the Planck time,
the energy densities and space-time curvature become so extreme that both gravity, general relativity, and quantum mechanics are equally important and intertwined. You absolutely need a quantum theory of gravity to describe what's happening.
And that's precisely the realm where string theory, or M theory, is supposed to apply. Yeah. Standard theories break down.
Exactly. GR predicts an initial singularity, infinite density, infinite temperature, right at time zero. Physics stops making sense.
Does string theory fix this singularity?
String theory inherently avoids the point-like infinities of GR because strings have a minimum size. So it's expected that string theory should resolve the Big Bang singularity, replacing it with some sort of finite, albeit extreme, state. However, describing precisely what that state is and how the universe emerged from it is still one of the biggest open questions in theoretical physics. We don't have the full picture yet.
The early universe might have also gone through phase transitions, like water freezing into ice.
Very likely. As the universe expanded and cooled dramatically after the Big Bang, it probably passed through several phase transitions. In these transitions, the fundamental forces and particles might have changed their character. For example, the electromagnetic and weak forces, which seem distinct today, are believed to have been unified into a single electroweak force at very high temperatures, with the symmetry breaking as the universe cooled. String theory could potentially describe even earlier transitions where gravity might have been unified with the other forces.
And string theory ideas might even explain why we have 3 large spatial dimensions.
There are some intriguing arguments related to that. Remember the wrapped strings in extra dimensions?
Yeah, the winding modes.
Calculations suggest that in universes with 3 or fewer spatial dimensions, wrapped strings are very likely to intersect and unwind each other. This interaction could potentially prevent those dimensions from expanding and becoming large.
But in 4 or more dimensions?
In 4 or more spatial dimensions, strings are much less likely to randomly intersect, like 2 random lines are unlikely to cross in 3D space. This lack of intersection might allow those dimensions to expand freely. So the argument goes, maybe string dynamics naturally favors a universe where exactly 3 dimensions grew large, while any others remain small and curled up.
That's a fascinating potential explanation coming from the theory itself, but what about the absolute beginning? The initial conditions?
That's the hardest part. As we said, string theory avoids the literal infinity of the standard Big Bang singularity, but it doesn't yet give us a definitive answer for how the universe actually began or what its specific initial state was just before expansion kicked off. Was there a before? Did time even exist in the way we understand it?
Is that even a question physics can answer? Or is it getting into philosophy?
It's right on the edge. Some physicists hope M theory will eventually provide an answer, perhaps describing a pre-Big Bang phase or a cyclical universe. Others suspect that the specific initial conditions might be beyond the scope of scientific prediction, maybe like asking physics to predict the outcome of a coin toss rather than the laws governing it. It's a deep, open question.
So wrapping this all up, where does this leave us with string theory and this grand quest for the ultimate theory?
Well, string theory, or M theory as its underlying framework, remains our most promising and mathematically consistent candidate for a unified theory that brings general relativity and quantum mechanics together.
It offers potential answers to some really fundamental questions.
It does, like why particles have the properties they do, related to string vibrations and extra dimensions, the quantum nature of gravity, gravitons as string modes, the microscopic origin of black hole entropy, and a framework for potentially resolving the Big Bang singularity and understanding the earliest moments of the universe.
There are still big challenges.
Huge challenges remain. We still lack a complete, non-approximate formulation of M theory. Most calculations rely on approximations or studying specific simplified scenarios. Without the full theory, it's incredibly difficult to extract precise, unique, testable predictions for particle masses or force strengths that we could compare directly with experiments at achievable energies.
And that lack of concrete testable predictions is a major criticism, right?
It is. String theory has been incredibly fruitful mathematically and conceptually, generating powerful new ideas and tools. But until it makes distinctive predictions that can be experimentally verified or falsified, it remains for some more of a theoretical framework than a fully confirmed physical theory.
There's also the issue of the landscape, right?
Yeah.
The vast number of possible universes.
Yes, that's another major challenge and area of a debate. As we discussed, there seems to be an enormous number, maybe 15,500 or more, of possible ways to curl up the extra dimensions, different Calabi-Yau shapes and other configurations. Each configuration would lead to a different universe with potentially different particles and forces a different set of physical laws in the large dimensions.
So string theory doesn't predict our specific universe, but rather a huge landscape of possibilities.
That seems to be the current picture. Our universe, with its specific particle masses and force strengths, would just be one particular valley in this vast landscape of possible universes.
If that's true, it raises a huge question. Why this valley? Why are the fundamental numbers defining our universe, the mass of the electron, the strength of gravity, exactly what they are, seemingly fine-tuned for complexity in life?
This is one of the deepest mysteries we face. If the landscape picture is correct, string theory itself might not provide a unique answer. One controversial line of thought is the anthropic principle,
Which basically says,
in a multiverse containing all these possible landscapes, maybe life can only arise in universes with properties like ours. So the very fact that we are here to observe the universe biases our observation toward those life-friendly properties. We couldn't exist in the other valleys to ask the question.
that feels a bit unsatisfying to some physicists, doesn't it? Like giving up on a fundamental explanation.
It does feel unsatisfying to many, yes. Other ideas propose physical mechanisms that might select our universe, like Lee Smolens's idea of cosmological natural selection, suggesting parameters evolve to maximize black hole production, as black holes might spawn new universes, but these are highly speculative.
So the quest is definitely far from over.
Far from over. Physicists are working intensely from many angles, trying to better understand M-theory mathematically, looking for potential observational signatures in cosmology or particle physics, like finding supersymmetry or evidence of extra dimensions, exploring the implications of the landscape, and developing alternative approaches to quantum gravity. The goal remains to see if string theory M-theory can truly fulfill its promise as a theory of everything, explaining not just how the universe works, but ultimately why it is the way we observe it.
Wow. We have covered a lot of ground today. From the smallest imaginable strings through warp space-time, extra hidden dimensions, the absolute weirdness of the quantum world, and towards this possibility of a single, maybe elegant, theory that could describe it all.
This deep dive really does highlight how physics keeps pushing the very boundaries of what we can even conceive, doesn't it? Constantly seeking that unified, fundamental description of reality.
It's genuinely amazing to think that these ideas, tiny vibrating strings dimensions curled up smaller than anything we can imagine, could actually be the key to uniting the laws of the vast cosmos with the rules of the minuscule quantum realm.
It's a breathtaking prospect, but as we've seen, the biggest questions often lead to even deeper mysteries. We've made progress on black hole entropy, but the singularity remains. We have a framework for the early universe, but the initial conditions are elusive. We have a candidate theory, but maybe a vast landscape of possibilities instead of a unique answer.
Yeah, those fundamental questions remain. The true nature of singularities, the conditions right at the beginning, and whether physics can ultimately explain why all the numbers defining our reality, the constants of nature, are precisely what they are.
Exactly.
So here's something to maybe leave you pondering as we wrap up. If the very fabric of space-time can tear and mend itself, as string theory suggests, and if the number and shape of dimensions might not be fixed, with huge dimensions potentially being equivalent to tiny ones, what does that truly tell us about the fundamental nature of reality itself? Is the solid, predictable universe we perceive just one possible state, maybe even an illusion emerging from a much stranger, more fluid quantum gravitational foundation? Are we just one possibility out of an unimaginable number in a vast cosmic landscape?
That's a fitting thought to mull over. What is space? What is time? What is stuff? String theory challenges our deepest intuitions about all of them.
Indeed. Well, thanks for joining us for this deep dive into the fabric of reality.